Take a big, deep breath in. Now that you've filled your lungs with oxygen, let's think about where that molecule is headed next. I'm Tyler Farah, and this is Oxyhemoglobin Dissociation. In this lesson, you'll learn fundamentals of the oxyhemoglobin dissociation curve. This is how scientists combine mathematics with oxygen transport in your blood. And you'll know you've mastered this topic when you can plot that curve and also predict how changes to your blood might change that curve. Take a moment and read through this question stem right now. This question stem exhibits exactly the kind of thought process that you're going to hone in medical school and beyond that. That is, doctors understand how a patient's physiology normally works, and then that allows them to go on and understand how a chemical or a drug or an altered state might change that normal physiology. So that's exactly what we're going to do here. Let's look first at how hemoglobin normally works, and then we'll take a look at how carbon monoxide might disrupt that. Let's start here. Hemoglobin is the molecule that binds oxygen and carries it in your bloodstream. In a drop of blood, you have 500 million red blood cells, and each red blood cell carries around 250 million hemoglobin molecules. And then each hemoglobin molecule has 4 subunits, so in a single drop of blood, there are around 500 billion available oxygen binding sites. What the y-axis tells us is the percent of those oxygen binding sites that are bound to oxygen. This is a really useful number. Consider this question. When the percent of hemoglobin saturation number drops, when we go down the y-axis, that means less of those sites are binding to oxygen. So if oxygen isn't binding to hemoglobin, where is it going? What is it doing when it's not bound to hemoglobin? When oxygen unbinds hemoglobin, it moves into the surrounding tissue so that it can be used for metabolism. So the y-axis basically tells us how much oxygen is in the blood. When that number is high, there's a lot in the blood. And when saturation is low, it's because oxygen has left the blood to supply the tissues. That's where the x-axis comes into play. This tells us how much oxygen is already in the surrounding tissues, measured as a partial pressure of oxygen. So here's another question to consider. What kind of relationship would you expect between these two variables? That is, when the PO2 of the surrounding tissue is already high, when that tissue already has oxygen, what effect will that have on hemoglobin oxygen saturation in the blood? You'd expect some kind of a direct relationship between the x and y variables. This is because a high PO2 in the surrounding tissue means that the surrounding tissue already has oxygen. And so oxygen will remain bound to hemoglobin in the blood instead. If you're already pretty familiar with this curve, though, you might be thinking, that's not what this curve looks like, though. And in fact, the prompt question even tells us that the final curve will be sigmoidal or S-shaped. That's because there are 2 factors that influence the shape of the curve to make it deviate from a straight line relationship. The first factor is cooperative binding. So what is cooperative binding? Cooperative binding is a phenomenon involving the 4 subunits of hemoglobin. Basically, when oxygen binds to one subunit, that induces a conformation change that allows the next oxygen molecule to bind more readily, and so on, until that hemoglobin has 4 oxygen molecules bound. Similarly, when a single oxygen jumps off a hemoglobin, it reduces that hemoglobin's oxygen affinity, so the next oxygen molecule jumps off as well. The net effect is that each hemoglobin molecule tends to be either fully bound to oxygen or fully unbound. Remember, we're talking about a population of 125 billion hemoglobin molecules per drop of blood. Within that population, you're going to find hemoglobin bound to 1 oxygen or 2 or 3, but for a given hemoglobin molecule, if the conditions are right for it to bind 1 oxygen molecule, then it'll most likely go ahead and bind 3 more pretty quickly thereafter. So at a population level, what this means is that as oxygen molecules start to bind to hemoglobin, it increases the rate at which more oxygen can bind. Now a question for you. How is rate usually represented in graphs? Rate is usually represented as a slope. So as cooperative binding starts to kick in, the slope of our curve shifts up and the curve gets steeper. Next, we'll see that the curve also eventually flattens out. This is not due to cooperative binding, rather it's due to a different effect, one you probably recognize from enzyme activity. Why would the curve eventually flatten out at higher levels of oxygen? The answer is saturation. It's a lot like musical chairs. Once the majority of the binding sites are taken up with oxygen, any remaining oxygen is left hunting for an available site. The rate at which oxygen molecules pair with oxygen binding sites drops, so the slope of the curve flattens out. Now we can apply this to physiology. For example, blood passes through the capillaries of the lungs, a very oxygen-rich surrounding tissue. What would you expect the percent hemoglobin saturation to be? The lungs have a PO2 around 100 millimeters mercury, which is the upper bound of our graph. And as you might expect, hemoglobin loads up with oxygen as it passes through the lungs. This is as close to full oxygen saturation as we get. 500 billion oxygen binding sites per drop of blood, and passing through the lungs, 97% of those will bind up with oxygen. Now consider resting muscle, for example. There's a huge drop in PO2 from the lungs to resting muscle. The PO2 of resting muscle is around 40 compared to 100 in the lungs. What effect would you expect this drop to have on the amount of oxygen that remains bound to hemoglobin in the blood? You would probably expect that a drop in PO2 from 100 in the lungs down to 40 in resting muscle would be accompanied by a drop in the amount of oxygen that remains bound to hemoglobin. And that's correct. After all, even resting muscle needs a steady stream of oxygen. But the drop isn't so big as you might expect. In fact, where 97% of the oxygen binding sites were saturated in the lungs, we're down now to 75% saturation as blood passes through resting muscle. If a drop of blood has 500 billion oxygen binding sites, still 375 billion of those will have oxygen bound. This means that your blood has a natural reserve of oxygen when you're at rest. And think about it. If I asked you to hold your breath, you could probably go for 30 seconds or more because of that oxygen reserve. Graphically, evolution has built this system so that resting muscle is above the big drop in that sigmoidal curve. It's just at the edge of that drop, but still safely above it. But now consider active muscle. Active muscle has a huge demand for energy, so it has a huge demand for oxygen. How does the oxyhemoglobin curve ensure that active muscle gets the oxygen that it needs? Notice that just a small shift in PO2 will send us skittering down the steep part of the curve. And that's exactly what happens when you start using your muscles. Active muscle has a PO2 around 20, so about half that of resting muscle. But notice that just making that small shift in PO2, suddenly hemoglobin saturation plummets. As you start running or swimming or weightlifting, oxygen just dumps off hemoglobin and into your muscles. In fact, if you've ever exerted yourself to the point where you physically cannot do one more rep or sprint one more step, the PO2 in physiologically exhausted muscles is all the way down to around 3 millimeters mercury. At that point, you physically have no more oxygen reserve in your blood, and so you have to stop. Now let's see what carbon monoxide poisoning does to this curve. We're told in the prompt question that carbon monoxide is going to cause both a left shift and also it's going to flatten out the top of the curve. So it appears that carbon monoxide influences both factors, both the shift up initially and then the flattening out later. We can explain both these effects using principles borrowed from a similar but different subject, enzymatics. We see that carbon monoxide increases the affinity of hemoglobin for oxygen. One carbon monoxide binds to one subunit, and then the other subunits have a greater oxygen affinity. Well, in enzymatics, how is an increase in enzyme substrate affinity depicted graphically? In enzyme substrate kinetics, an increase in affinity is graphed as a left shift of the curve. And it's the same here. The carbon monoxide curve is left shifted relative to the normal curve. How about the other factor? In the carbon monoxide curve, it flattens out more rapidly. Well, remember that the curve naturally flattened out due to saturation. So why would the carbon monoxide curve saturate more rapidly? The carbon monoxide curve flattens out more quickly because carbon monoxide binds essentially irreversibly to oxygen binding sites. This blocks oxygen from binding. But as a final note, this isn't actually what makes carbon monoxide so dangerous. In fact, only about 1 in 8 of your hemoglobin binding sites need to be bound to carbon monoxide to have a potentially fatal case of carbon monoxide poisoning. Think about it. That means that 7 out of 8 of your sites are still available. In a drop of blood, that means you've still got 437 billion available oxygen binding sites. That's plenty of oxygen for you to continue to survive. No, what makes carbon monoxide dangerous isn't that it blocks oxygen from binding. It's that once oxygen is bound, the oxygen can't unbind. The curve works normally because resting muscle is at the top of the curve and active tissue is at the bottom. That's the mechanism that ensures that tissues that need oxygen actually get it. The problem is carbon monoxide shifts that curve so that the oxygen remains bound even when tissues desperately need that oxygen supply. I want to end with a quick story from my own prep for the MCAT. About 2 weeks before the test, I took a practice exam. They had a passage on oxyhemoglobin dissociation, and I got destroyed. But I learned from my mistakes. I spent the afternoon studying this topic, and on my actual exam, sure enough, there was a passage about the exact same principles I'd studied. So that taught me an important lesson that I want to pass along to you. Wrong answers today make right answers on test day, provided that you learn from your mistakes.